Hello class, let's take a look at molecular geometry. Why study molecular geometry, you're probably thinking? Well, that's because the shape and the size of a molecule will affect its strength, polarity, its properties, how it behaves. It really does explain a lot, and you're going to see this come up throughout the course. You know how to do Lewis structures, but Lewis structures don't show the shape of a molecule. Shape is determined by bond lengths and bond angles. So what we're going to review in this quick little PowerPoint, well, it's probably not quick, but what we're going to review, electron versus molecular geometry, shapes, exceptions, valence shell electron pair repulsion, VSEPR, hybridization, and most of this is a basic review of what we did in regular chemistry. There's a few little new things thrown in, but for the most part, it's just a review of what we've done before. Two different terms you need to be familiar with are electron geometry and molecular geometry. Well, these are based on something called the electron domain. So let's just first review VSEPR. VSEPR stands for valence shell electron pair repulsion. Basically, what you need to remember about that is that electrons repel each other. So if you have, like on this picture here, those electrons sitting on S, that's just a gigantic balloon of negativity. And those electrons are pushing on electrons nearby, and it's changing the shape of that entire molecule. What do we mean by an electron domain? Well, first you need to focus on one atom. So for right now, let's just focus on the sulfur, the S. An electron domain can be a bonding pair of electrons. So between the S and the single bond to the O, that would be an electron domain. Non-bonding pairs of electrons is a domain. So those two dots sitting on top of the S is a domain. That double bond between the S and the O, that's considered one domain. Even though there's two pairs of electrons, it's just one domain. And those domains, because they all have electrons, are going to repel each other. That's going to affect the shape. And basically what happens is the atoms are going to arrange themselves in a way that minimizes repulsions. So what I always tell basic chem kids is focus on the center atom, or whichever atom it tells you to focus on. So in this case, focus on S. And then count how many things are around S. Is there anything to the left? Yep. Anything to the right? Yep. Now I'm up to 2. Anything on the top? Yes, the dots. Anything on the bottom? No. It has 3 domains. So I don't have water on here, but you guys know that you have O in the middle with an H on either side. And O has 2 dots on top, 2 dots on bottom. Is there something on the left? There's an H. Something on the right? There's another H. Something on the top, a pair of dots. Something on the bottom, a pair of dots. So water would have 4 electron domains. Now that you know how to count electron domains, you can determine the electron geometry as well as the molecular geometry. For electron domain geometry, count the total number of electron domains. And then I'm going to show you here in an upcoming slide, you go to a reference table or memorize, you'll know what it is. So if you look down at that diagram, we've already decided that S has 3 domains. There's something on the left, something on the right, something above. That's 3 domains, and 3 goes with trigonal planar. Molecular geometry is not necessarily the same as the electron geometry. You start with the electron geometry. To go to the molecular, you need to remove any non-bonding pairs of electrons. So if I had a model, which I don't think I do at the moment, you've got S, oxygen, oxygen, and you're going to have something on your model for those electrons that are sticking out of the S. So 1, 2, 3, trigonal planar. You're going to pluck off those electrons that are not bonded to anything, and trigonal planar becomes bent. So when there are no non-bonding pairs of electrons, there's no dots hanging out anywhere, then your molecular is going to be the same as your electron geometry. Picture methane, CH4. C in the middle, H on all 4 sides. It's going to be tetrahedral both ways. while I've already mentioned what you need to do, let's just review really fast. In order to figure out what a molecule shape is, number one, draw the Lewis structure. You must draw it correctly. So remember, count the number of valence electrons there should be, do a skeleton. Everybody who gets 8, give them 8 electrons. Go back and double check. If you need to, throw in double and triple bonds. You might also want to look at the formal charge and see which one's correct. But once you have an accurate Lewis structure, count your electron domains. That's your electron geometry. If you need to, remove any pairs of dots and go from the electron geometry to the molecular geometry. And you'll see on the next couple of slides what those shapes are. Let's look at the basic electron domains. By the way, this is in your book. You can also find these resources online. The first thing you want to look at is how many electron domains are there. If there are only 2, for example, CO2, you've got C in the middle, O on either end. You have 2 electron domains. 2 will always be linear. And what does that mean? There's 180 degrees from O to O. If there are 3 domains, now you have trigonal planar, 120 degrees between the atoms. 4 is tetrahedral with the bond angle of 109.5. If you have 5 things like PCl5, you're going to have trigonal bipyramidal. Now it's kind of weird, it's kind of hard to see in this picture, but we'll go over it in class. If you look at that picture, there is a pyramid on top and it has a triangle base. There is also, flip it over, a triangle pyramid on the bottom. Trigonal bipyramidal, 2 pyramids. And there's 2 different angles going on here. You've got 120 degrees on the triangle in the middle and 90 degrees. Sorry, my puppy's playing. And then the last one is 6 electron domains. You have octahedral, 90-degree angles between everything. Now this one threw me for a loop. I'm like, oct means 8, and there's 6 things. Somebody get their prefixes mixed up? Well, if you look at this, what you see is a square in the middle. So you have a square pyramid on top and a square pyramid on bottom. Well, a square pyramid has 4 sides. 4 up here, 4 down here, 8. And that's where they get octahedral. So let's just review again. How do you go from electron to molecular geometry? Find how many electron domains there are. That gives you the electron geometry. Remove any of these balloons that are there because of the non-bonding electron pairs, and then what shape remains. On the next slide, we'll look at all those exceptions. Before you panic, I would like to point out that we will play with the models, just like we did last year, and for some reason, playing with the models just makes this all click. Now, this is in your textbook. There are all sorts of resources online, but if you want to pause and write this down, it's not a bad idea. There is something to be said for writing things down and making that connection in your brain. So let's look at how you read this table first. So the first column is just how many electron domains are there. So if you have something like CO2, there are 2. There's something on the left, something on the right, nothing above or below the carbon. That is linear. There are 2 bonding domains. That means there are 2 things connected to the C. There are no non-bonding domains. There are no electrons pairs just sitting on that carbon. So you get linear. When you have 3 electron domains, you have trigonal planar. If all 3 are bonded and you don't have any non-bonding, so you don't have any just balloons of negativity sitting there, you get trigonal planar. And the example is BF3. But what if you have 2 bonding domains and 1 non-bonding, as in the case of the NO2 ion? Well, that purple thing on top it's just 2 pairs of electrons that aren't bonded to anything. And it acts like a negativity, this balloon of negativity. And what's happening is that balloon of negativity is pushing on those other electrons. So not only does the geometry go from trigonal planar to bent, but the bond angle changes. Initially you have 120 degrees, now you have about 117. It's going to decrease. Now what if you have 4 electron domains? We know that's tetrahedral. If you have NH3, that N has 3 things bonded to it and 1 thing not bonded to it. That one balloon of negativity is going to change the shape from tetrahedral to trigonal pyramidal. So what I would recommend is that when you make the Lewis structure for NH3, build a tetrahedral. Then pull one of those atoms off, and you will see trigonal pyramidal in 3D. What if you have water? Oxygen has two balloons of negativity. Again, start with tetrahedral, pull two off, what's left? Bent. Now that is not the same bent that you saw in trigonal planar, and here's why. Tetrahedral has bond angles of 109.5. Trigonal pyramidal, it goes down to 107. And when you go to bent, it's actually 104.5. All right. Now it gets a little bit more strange when you get to trigonal pyramidal or bipyramidal. And I thought I had my model kit at home, but I think I took them back to school. What you have here is you have in the middle a triangle, and you have a stick going through that triangle, and you've got something up here and something down here. You can kind of see that on that diagram, the little blue triangle in the middle. So those three in the middle are a triangle. They're planar. They're all on one plane with this spike going through. So if you have PCl5, you have trigonal bipyramidal. Well, what happens if you have something like SF4? You have one balloon of negativity. And this took me a little while to figure out. When you remove atoms, you remove them from that inner triangle. Well, when you take one off, you literally get seesaw. And if you play with the model, you'll see how it becomes seesaw. What if you have two balloons of negativity? Pull another one off from that triangle. All that's left is T-shaped. Might have to turn your head to see it, but it's T-shaped. What if you remove all three? What's left? Linear. Octahedral's a little bit easier. If you need to pull off a balloon of negativity, you pull it off the top or the bottom, leave the square alone. I don't know if you can see that, but there's a square in the middle, and then one on top and one on bottom. So when you remove one, you get square pyramidal. When you have to remove the top and the bottom, you get square planar. And it really does start to just drill into your head, especially if you play with the model kits. Yes, you do need to memorize these. Yes, you need to know all of the exceptions this time. I mentioned this before, but I just wanted to go over it one more time with you. As the number of non-bonding electron pairs increases, the bond angle decreases. And this is because you've got this balloon of negativity, they're pushing on the nearby electrons, they're taking up more space, and they're going to squish those other atoms a little bit closer together. So here's the example. Methane has the normal 109.5 degree separation between the two H's. Ammonia, though, goes down to 107, and water with the two balloons of negativity drops it down to 104.5. Up until this point, we've focused on just the center atom. Can you look at a much larger molecule? You can. You need to predict geometry at each atom. And I just want you to know right now, textbooks are notorious for giving you a Lewis structure that's not always complete. Like they'll show an O bonded to something and bonded to something, but they don't always put the dots on the O, or they don't always add dots to an N. So be really careful. Don't assume that the Lewis structure is complete. But take a look at this diagram. The two black dots are carbon. The white ones are probably H, and the red ones are probably O. So let's look at the very first carbon all the way on the left. There are 4 domains around it. There's 3 white things, and then there's a black thing. 4 domains. 4 is tetrahedral. So right there you have a tetrahedral shape. Go to the next black dot, the next carbon. Well, this one only has 3 domains. It's connected to a black dot, it's connected to a red dot, it's connected to a red dot. So you have 3. 3 is going to go with trigonal planar. And then the oxygen that's connected to 2 things, well, it's connected to the black dot, it's connected to the white dot. So most kids will just jump to, 2 domains, it's linear. No. You're forgetting that oxygen in this case is going to have 2 pairs of electrons just sitting on there. So tetrahedral is going to become bent. I know we've already talked about dipoles and polar and whatnot, but just keep in mind that the shape is going to let you know whether or not something is polar. So take a look at the very first example, CO2. Oxygen is pulling the electrons away from carbon. But because you have one pulling this way and one pulling this way, just like tug of war, you have equal and opposite pulling. They cancel out. There is no dipole, there's no polarity on that, okay? Overall. But water's a little different. Because it's bent, it's got that unique shape, the oxygen is pulling a little unequally, and that lets the oxygen be negative and that lets the H be positive. So pay attention to your sizes and directions, okay? By the way, that was Bella in the last video you heard. I just wanted to just show you a little bit of a picture here for a moment. And I want you to think and keep in mind that when electron pairs bond, there's a region between the atoms where the orbitals overlap, and the non-bonding electron pairs are in regions of space. So look at H2. Two H's come together. The electrons are in between the two nuclei, and they're sharing some space there. Those orbitals are overlapping. In HCl, something a little different going on. Well, H just has a 1s. The vacant spot in chlorine is going to be in one of the 3p orbitals. So the 1s orbital will overlap with the 3p orbital. Chlorine and chlorine, again, where's the open space? It's in one of the 3p orbitals, and so the overlap will occur right there. We are going to see this graph in one of the POGLs that we do, and it's a very strange looking graph, very bizarre, kind of complicated, but once you understand what it's showing you, it actually makes a lot of sense. This graph shows you what happens as a molecule forms. On the x-axis is how far apart these two atoms are, and then on the y-axis is the potential energy, okay? Let's start all the way over on the right. What you have here are two H atoms very far apart. They don't feel anything, they're not attracting, they're not repelling, they're just so far apart they don't even realize they're anywhere near each other. And this is why the potential energy is sitting around 0. But as you go toward the left, I know I'm going backwards, those atoms get a little bit closer together. And as they start to get closer together, you've got some attracting going on between the nuclei and the electrons. You've also got some repelling going on between the electrons. Well, there's a sweet spot at that 0.74 angstrom, that the bottom of that curve. That is where the attraction and repulsion is minimized, maximized, however you want to put it. That's the sweet spot where the two atoms can bond. So you've got attraction going on, you do have some repulsive forces going on, but they're all balanced out. And that is at a minimum potential energy. Why is it at a minimum? Well, because that's where it wants to be. It's stable. There's no massive amounts of attracting or repelling going on. It's nice and stable. So there's not a lot of potential energy. It's just like a rubber band sitting on the table. There's no potential energy. But as you keep going to the left, those atoms get so close together that there's this extreme amount of repulsion going on. It's like stretching that rubber band. All you have to do is let go and it fires across the room. So as two nuclei are super close together, now this is the very, very first part of the graph, you have an extreme amount of potential energy. At the sweet spot where they bond, you have the lowest amount of potential energy. And when they're super far apart, potential energy is about 0 because they don't even know they're there. Just in case you keep hearing noises, I've got 4 dogs roaming around. I have a 22-year-old son roaming around, and I have a clock that sounds like a bomb. Anyway, hybridization. We assume that the central atom's orbitals mix to form new orbitals with the atoms that are bonded to it. We call this hybrid orbitals or hybridization. I will show you this and explain it on the next slide. And the shape of a hybrid orbital is different from the original. You guys know that S is spherical. You know that P orbitals look like dumbbells. Well, when an S combines with a P, you get a totally unique shape. It's kind of neat. And by the way, all this is based on mathematical, statistical, icky math. Just trust me on this. And we call it hybridization. In this class, you need to know about 3 different hybridizations: SP, SP2, and sp3. And there are other ones, and they're really easy, and we will do them when we do this one lab because it's really not that difficult. But AP Chemistry simply wants you to know sp, sp2, and sp3. So let's take a look at what's going on. What if we want beryllium, Be, to bond to F? If you take a look at the picture where it says Be atom in the ground state, Be has 4 electrons. We find 2 in 1s, and we find the other 2 in 2s. Aren't both of those orbitals full? Well, how does it bond? That doesn't make sense. And then take a look at F. We want to stick an F on either end of the Be, okay? F has a full 1s, a full 2s, and it has 5 out of 6 in the 2p. Well, clearly there's a space to put an electron in the F. How are we going to get it to bond to the Be? Well, the theory is, what if one of those electrons from the S moves up to the P? Now we can do some moving around. So what we call this is sp hybridization. We take an s orbital, we take one of the p orbitals, and we blend them together. And you get this, still a dumbbell shape, but you get a really small piece and a really big piece. And the really big piece is the piece that's going to stick out on the end away from each other. And I'll show you on the next slide what a BeF2 molecule will look like. Oh, and for the record, he's 22 and a half today. This is what BeF2 would look like. Now, in the middle is Be, and remember you had that hybridization going on. All you see is the bigger lobe. So I went ahead and showed you that small lobe down there. It's kind of hard to see. And that big lobe is going to attach to the fluorine, just to give you an idea of what this starts to look like. So let's talk about sp2 hybridization. By the way, I didn't point it out. sp is always going to be what you would call linear. And again, just go back to counting how many domains you have. This and this, sp, 1, 2, okay? sp2, spp is 3, trigonal planar. So when you mix a certain number of atomic orbitals, you get the same number of hybrid orbitals. So take a look at this picture. If you have one s and 2 p's, you have an s and 2 p's, right? So you're going to make 3 hybrids. If you start with 3, you're going to make 3. If you take a look at that, this kind of gets a little bit more into the depth that we need to get into, but these will arrange in a way to where those small lobes all point to each other. The bigger lobes will point away from each other because that's where we find more electron density. And again, they want to repel and be farther apart. But take a look. What's the shape? Trigonal planar. So sp2, 3 things. spp, 3 things. Trigonal planar, which means we have 120 degree angles. And the last one is sp3 hybridization. So you take one s, you take all 3 of the p orbitals. Remember, there's 3 different ones, one on the x-axis, one on the y, one on the z. And because you have 4 things, an s and 3 p's, you're going to make 4 hybrid orbitals. And you can see there the s and p's we started with. You can see what they look like, and you can see how they get arranged together. And what do you get? Tetrahedral, 109.5 degrees in between them. Like I said, we're not going to go beyond sp3, although it's really easy, and I will actually have you do it when we do our lab. It would be sp3d, sp3d2. I mean, it's not brain surgery. But it's best not to use hybrid orbitals to explain those hypervalent molecules. What do I mean by hypervalent? Trigonal, bipyramidal, the octahedral, the things that go beyond 8, the octet rule. You have to start hybridizing with the Ds, and AP chemistry just doesn't make you do that. But here's the reason why it's an issue. The D orbitals are actually at a much higher energy level, and so you start getting into some really weird issues going on. If you take an upper level chemistry class in college, I guarantee you'll get into this. And it's really not that hard, and it's actually kind of interesting. But for now, we're just going to end with sp3. Let's just pause for a moment and do a really quick review. SP, count 2 things, linear. SP2, count 3 things, trigonal planar. SP3, Four things, tetrahedral. This is useful for things that have an octet or less. Doesn't work for hypervalent molecules very well. And how do you get there? Again, draw the Lewis structure correctly. Figure out the electron geometry. Figure out the molecular geometry. Again, if you've got like water is tetrahedral to begin with, so we would say sp3. Really not that bad. We will put this into practice both in some worksheets, some hands-on problems from the textbook, and of course our lab. So let's just do a really quick example. Let's say I gave you NH3. First, Lewis structure. Well, N has 5 valence electrons. Each of the H's is 1, so a total of 8. Put N in the middle, put the H's around it. N needs 8, so give it a pair of electrons. So we have something on the left, right, top, bottom. We start as tetrahedral, pull one off, it becomes trigonal pyramidal. But as far as the hybridization goes, it's based on the electron geometry. So if we have tetrahedral for the electron domains, then we're going to have sp3. My son would like to be just momentarily involved with the video. Everybody say hi. By the way, he graduated college and is going to be working on a master's coming up. So here's the new part of AP chemistry or college chemistry that we haven't yet talked about. Sigma and pi bonds. And they go back to basically single, double, and triple bonds. Well, a sigma bond is the strongest type of covalent bond there is. It is what is happening in between two nuclei. So if you look at that picture where it says sigma bond, imagine a line connecting two nuclei. We call that the internuclear axis. And what that means is that there are a lot of electrons found in that space, very, very strong. So a single bond is going to have a sigma bond. In fact, every kind of bond is going to have a sigma. A double and a triple will also have that bond. Once you get beyond the single bond, we have what are called pi bonds. And I'm going to show you some more pictures coming up that'll make it make a little bit more sense to you. But a pi bond results from some overlapping of two p orbitals. And what they do is they cross over above and beyond that internuclear axis and kind of connect two different atoms together. The electron density is not concentrated on the internuclear axis, it's above. This is a much weaker bond, but we call it a pi bond. By the way, Josh will be working on a master's in economics. I know, I don't know why. He took AP Chem with me. He liked it, he did well, but he didn't choose science. Let's just review very quickly, and then I'm going to show you on the next couple slides how this works. A single bond simply has one sigma bond. A double bond has a sigma and a pi. A triple bond has a sigma and two pi bonds. And yes, you need to know this. You need to be able to count these, okay? So let's look what's happening at a double bond. And by the way, this is in your textbook, but hopefully this makes a little bit more sense than the textbook. The first thing I want you to see is right there, okay? By the way, this is carbon right there, and then that, and that. Those are hydrogens. And down here, you can see the hydrogens. They're kind of a darker color. We know that there's a bond between carbon and carbon on that internuclear axis. This is your sigma bond, very strong. And then you come down here. So carbon also is attached to a hydrogen. You have carbon attached to a hydrogen. You have a carbon attached to a carbon. Well, you guys know that carbon needs to have a total of 4 bonds. Well, that's only 3. So we know that if we were to draw C2H4, we would have a double bond. Well, how does that double bond occur? Well, do you see, let me change color here. Do you see that p orbital, that p, and then this p? Well, they're not attached to anything. They're just p orbitals floating out there. Well, what happens is this connects over here, this connects over here, and this gives us what's called a pi bond. Somewhere in this gigantic thing are 2 electrons. So we have 2 electrons here in the sigma bond and 2 electrons in the pi bond. And that's how you get a double bond. Let's take a look at how a triple bond forms. This is going to be C2H2. There's the carbon, there's a carbon, there's a hydrogen, and there's a hydrogen. So what's happening here? Let's see if we can get this a little bit brighter. We have carbon bonded to carbon, and then carbon bonded to hydrogen, carbon bonded to hydrogen. Well, if you look at that first carbon right there, carbon only has two things around it. We know it needs to make 4 bonds, all right? So how does that happen? Well, first, the carbon to carbon is our sigma bond. Now I want you to notice what's different from the last slide is that there are 4 on each atom p orbitals that are not attached to anything. It's kind of hard to see the one because it's like on the back side, all right? But these p's are all going to come together to make 1 pi bond, just like you saw in the last slide. And then there's another 4 kind of going through the model, kind of like on the z-axis coming in and out of the page, and that's another pi bond. So you have the sigma between the 2 carbons, then you have a pi bond that goes up, over, down, in here, and then you have one that comes out of the page and into the page. Triple bonds have 1 sigma and 2 pi bonds. On a previous video, I talked about resonance. Sometimes you can draw a Lewis structure in one of 2 ways. Well, take a look at benzene. You can draw benzene with the 3 double bonds right there, or you can draw benzene with the 3 bonds right there. That's resonance. You could draw it either way. Well, one of the easy ways with benzene is just to draw the structure and draw a circle in the inside. And the circle just simply means it can go either way. And probably are found in that way. Well, we call this delocalized electrons. And what that means is the electrons, they can move. They've got some freedom in there. And this changes the rigidity, that's hard to say, of a molecule. I just wanted to point that out to you, and we will talk about it a little bit more in some of our work. Just a very quick moment on molecular orbital theory. Your textbook and most textbooks go into this. AP Chemistry says you don't need it. I actually had to learn this for one of my graduate classes and actually kind of enjoyed it. It was kind of weird. Really not that challenging. It just looks really scary. But it's a theory that describes covalent bonding with a much wider application. It also explains some properties and phenomena that we witness, but we can't explain with just Lewis or Vesper. This isn't required in AP Chemistry, so we're not going to do it. But if you do want to take a look at it, it is in your textbook. It's kind of interesting. While you don't need to know molecular orbital theory, you do need to know about bond order, okay? You find the bond order by taking 1/2 times the number of bonding electrons, subtract the number of anti-bonding electrons, or the number of bonding electrons minus the number of anti-bonding electrons, and then divide it by 2. Well, we haven't really talked about this because we didn't need to get into molecular orbital theory. But when you do a molecular orbital diagram, some of those electrons are called bonding electrons, and then the other ones are put into an anti-bonding orbital. So this is actually part of one of my homework assignments that I had to do for one of my classes. And what I'm demonstrating here is the O2 positive ion. So we have oxygen right here, and I'm only focusing on the p orbital. Oxygen has 6 valence electrons. 4 of them are in the p orbital. So 1 is in 1 p orbital, 1's in 1 p orbital, and then 2 are in 2 of them. And then we're going to pair that with an O positive. Well, that means it's lost an electron, so that's why there's only 3 electrons right here. So I've got a total of 4 right here and a total of 3 right here. So you take 1 from here and 1 from over here and you put them down here. These are your bonding electrons, okay? Bonding orbitals. And you keep doing that. So I have a total of 7 electrons. Well, 6 of them go down here. 1 of them goes up here in the anti-bonding area. So if you think about this, what do we have? We have a total of 6 bonding minus 1, that's 5, divided by 2, you get 2.5. Over here, this little piece right here, this is what I actually included in my homework assignment. Well, I kind of did the math in pieces. You have 6 bonding electrons, so I already divided that by 2, and you get 3. Well, you only have 1 non-bonding, or 1 in the anti-bonding, sorry, and that's a half. Well, what's 3 minus a half? 2.5. Yeah, so this has a bond order of 2.5. Huh? Weird, right? So what does this mean? If you get a bond order of 0, there's no bond. If you get a bond order of 1, you get a single bond. Bond order of 2, double bond. 3 is a triple bond. 2.5, see, I told you, molecular orbital theory is kind of weird. It explains some other weird properties like paramagnetism and stuff. We're not going to get into it, but you do need to know how to calculate bond order. And you're going to get bond order to equal 1, 2, or 3. You're not going to get these weird things. One more thing, what does no bond mean? I'll give you an example. If you did the molecular orbital theory for Ne2, neon with a 2, you're going to find that doesn't happen. You're going to get a 0. Well, what does that mean? It means Ne doesn't bond to itself. Ne is just Ne. It's really kind of interesting. If you take an upper level chemistry class, I guarantee you'll get into this. There are tons of resources online that help explain it in case you don't have a great professor or your book just doesn't make sense. Now, go tackle your homework.